Hello everyone. Have you ever noticed how carrying a bucket underwater feels easier than carrying the same bucket on land? Or why a balloon filled with helium rises quickly while one with air barely moves? The secret lies in the characteristics of upthrust. Upthrust is not the same in every case. It changes depending on how much of a body is submerged and the kind of fluid it is placed in. And most importantly, this upward force always acts at a special point called the center of buoyancy. Let's explore these properties step by step. First, the effect of volume. Imagine you push an empty can or a cork deeper and deeper into water. As you increase the depth, the water pushes back harder. Why? Because the more volume of the body that goes underwater, the more water it displaces. Mathematically, we say buoyant force F subscript B is directly proportional to the submerged volume V subscript sub. That means F subscript B equals rho times G times V subscript sub, where rho is the density of the fluid, G is acceleration due to gravity, and V subscript sub is the displaced volume. So, more volume underwater equals greater upthrust until the body is fully immersed. Next, let's talk about the density of the fluid. Imagine placing the same cork into beakers, one with water and one with glycerine. You'll notice the cork sinks deeper in water but less in glycerine. Why? Because glycerine is denser than water. For the same submerged volume, the denser liquid exerts a stronger buoyant force. The equation remains the same. F subscript B equals rho times G times V subscript sub. So, whether it's water, glycerine, or even mercury, denser fluids always push harder upward. That's why swimming in the Dead Sea, which is salt-rich and very dense, makes you float effortlessly. Now comes a fascinating detail. Where exactly does this upthrust act? It acts at the center of buoyancy, which is the center of gravity of the displaced liquid. For a uniform body fully immersed, the center of buoyancy coincides with the body's own center of gravity. But if a body floats partially submerged, the center of buoyancy lies below the actual center of gravity of the body. Look at the diagram. The weight W acts downward at point J, while the upthrust F subscript B acts upward at point B. For equilibrium, these two must be equal. F subscript B equals W. That's how floating stability is achieved. Let's test this idea in air. Drop a bunch of feathers and a pebble of the same mass. What happens? The pebble falls faster. Why? Because air exerts more upthrust on the large volume feathers than on the tiny volume pebble. Remember, F subscript B equals rho of air times G times displaced volume. Even though air is very light, its effect is noticeable on large, fluffy objects like feathers. But in a vacuum, there's no fluid at all, so there's no upthrust. That's why in a vacuum, both the pebble and feathers fall together at the same rate. Amazing, isn't it? Let's solve a quick numerical to make this crystal clear. Suppose a body has a volume of 200 cubic centimeters. We immerse it fully in water and then in glycerine. Water has density 1000 kilograms per cubic meter and glycerine has density 1260 kilograms per cubic meter. Step 1. Apply the formula F subscript B equals rho times G times V for water. F subscript B equals 1000 into 9.8 into 200 into 10 to the power minus 6. For glycerine, F subscript B equals 1260 into 9.8 into 200 into 10 to the power minus 6. Step 2. Compare results. The upthrust in glycerine is 1.26 times the upthrust in water. So, for the same body and same volume, the denser fluid provides 26% more upward force. That's the power of density in buoyancy. So, let's wrap it all up. Upthrust depends on two main factors, the volume submerged and the density of the fluid. It always acts vertically upward through the center of buoyancy, which is the center of gravity of the displaced liquid. This explains why feathers float more gently in air than pebbles, why we float more easily in salt water than fresh water, and why balance is achieved at a certain depth for floating objects. In short, greater volume, denser fluid, stronger upthrust. That's the crux of buoyancy. I hope you enjoyed this deep dive into the characteristics of upthrust. In the next session, we'll explore Archimedes' principle and see how these ideas expand into one of the most important laws in physics. Until then, keep observing how objects float and sink. Physics is all around you.